Let's talk about something that sounds, well, just plain wrong. Why are computers, these incredible machines of pure logic, actually kind of bad at math? I know, it sounds crazy, but if you've ever written a line of code, you might have seen the proof with your own two eyes.
Right, this thing. You ask a computer to add point 1 and point 2, and a lot of the time it gives you back something like 0.30000000004. Now this isn't a bug, your computer isn't broken. It's actually a clue that points to a really deep fundamental challenge at the heart of how pretty much every computer works.
So to really get what's going on here, we have to dig into the root of the problem. And it all boils down to this fundamental clash between the very finite world of computers and the, well, infinite world of numbers.
Think about it, right? Between any two numbers you can think of, say 0 and 1, there is a literal infinity of other numbers. But a computer? It only has a limited number of tiny switches, these bits, to try and represent all of them. It's like trying to write down every number that exists on a single small notepad. You just can't do it. You have to make approximations. And the secret to all of this is making those approximations as smart and predictable as possible.
You know, some of the early ideas for solving this ran into a huge trade-off. It was called fixed point representation. Basically, you had to decide where to lock the decimal point, and you were stuck. If you wanted to handle huge numbers, you needed a lot of digits before the decimal, which left you with almost no room for fractions. But if you wanted to be super precise with tiny fractions, you needed digits after the decimal, and you couldn't represent big numbers. It was this constant tug of war between range and precision.
For a long time, it was just total chaos. Every single computer maker had their own way of doing things, and none of them were compatible. Trying to share code was an absolute nightmare. But then, in 1985, a plan emerged to finally bring some order to all this madness.
Seriously, before 1985, you could run the same program on two different machines and get completely different answers. It was a mess. The IEEE 754 standard changed everything. It was like creating a universal language for numbers that nearly every computer on Earth speaks today. So what was this game-changing idea?
The big idea was something called a floating point number. And honestly, the core concept is something you probably learned in high school science, scientific notation. You know how you can write a massive number in a really compact way? Well, floating point numbers do the exact same thing, but they do it in binary. This lets the binary point float around to wherever it's needed, giving us that huge range and great precision all at the same time.
Okay, so let's pop the hood and see how this actually works. We're going to take a look inside a standard 32-bit floating point number, which programmers just call a float, to see the clever bits of engineering that make it all happen.
So, every 32-bit float is broken into three distinct parts. First up, you have a single bit for the sign. Easy enough. Is it positive or negative? Then, you have an 8-bit chunk called the exponent. This part is basically the power of 10 in scientific notation. It tells you how big or small the number is. And finally, the biggest piece, the 23-bit fraction, holds all the actual significant digits of the number. Now, the exponent has this really smart little trick. Instead of wasting a bit to say if the exponent itself is positive or negative, it uses a bias. It just adds a fixed number to every exponent, making them all positive. Why? Well, this lets the computer compare two floating point numbers really, really fast. It's a clever little performance hack.
And the fraction part has its own cool trick. You know how in scientific notation the first digit is always something from 1 to 9? Well, in binary scientific notation, that first digit is always a 1. So, since it's always a 1, why even bother storing it? The IEEE 754 standard just assumes it's there. This is called the implied 1, and it's this awesome hack that gets us one extra bit of precision completely for free.
But what happens when things go a bit sideways? You know, like when you try to divide by 0? Well, the folks who designed this standard thought about that too. They set aside a few special patterns of bits to handle all those weird edge cases gracefully.
Check this out. By setting the exponent bits to all zeros or all ones, the system can signal these special values. There's a code for 0, and, get this, there's both a positive and a negative 0. There's a code for infinity, for when a calculation gets way too big, and there's not a number, or nan, for when you do something impossible, like taking the square root of a negative number. And there's one last little piece of magic for numbers that are incredibly tiny, almost 0 but not quite. The system has a special way of handling them called denormalized numbers. It just allows for a nice smooth fade to 0 instead of just abruptly falling off a cliff. It's another one of those details that makes the system so robust.
So we have this amazing standardized system. It's incredibly clever.
But because it's always an approximation, it comes with some, let's say, quirks. And the most shocking one is that some of the basic math rules you learned in elementary school, yeah, they don't always apply here.
Okay, so here's the bottom line. In the world of floating point numbers, the order you do things in really matters. That rule you learned, the associative property, that says A plus B plus C is the same as A plus B plus C, it can totally break, especially when you start mixing huge numbers with tiny ones.
Let me show you. Let's take a massive number at 10 to the 10th power and add a tiny number to it, like 3.14. Because the computer only has so many bits for precision, that little 3.14 gets completely lost when it's added to the huge number. It's like adding a single drop of water to the ocean. It just vanishes in the rounding. So the result is basically just 10 to the 10th. You subtract that, and you get 0.
But now, watch this. Let's just change the order. We'll do the subtraction first. 10 to the 10th minus 10 to the 10th is of course 0. Then we add 3.14. The result, 3.14. So there you have it. Same numbers, different order, and a completely different answer. That's floating point math for you.
And that brings us all the way back to the beginning. If these numbers can't get basic addition right every time, does that mean the whole system is just broken?
Not at all. Floating point numbers are not broken. They are a brilliant practical approximation. They represent a smart engineering trade-off that allows us to work with a mind-boggling range of numbers using a finite number of bits. The rules might be a little weird sometimes, but they are perfectly consistent and predictable once you know them. It's not bad math, it's just a different kind of math. A kind of math that really made the entire modern digital world possible.